In today's video, we're going to use our understanding of electromagnetic waves and how they interact with different mediums for our problem Q1 through Q5. What we have here is we're given our electric field incidence and our frequency. We're looking for the problem Q1 first, so we're going to see what the reflected H field off the first surface would be. So we have our incidence wave hitting this surface, and we want to find our reflected HR. So to start off this problem, I would want to find omega first, and I would want to find this value, which is equal to the reflection coefficient. And the reflection coefficient represents the fraction of electric field being reflected at the boundary. All right? So to solve for omega, we can say omega is equal to 2 pi f, which gives us 2 pi times 15.92 gigahertz. Gigahertz is 10 to the 9, so we just denote that as 10 to the 9. And we get an omega of 10 to the 11. And we want to find the reflection coefficient. Our reflection coefficient equation would be N1 minus N2. So the refraction coefficient of the first medium and the second medium, and then N1 plus N2. This will give us 1 minus 4, 1 plus 4, which will give us a value of negative 3 over 5, or negative 0.6. And we know that N2 is going to be 4 because it's given. Index of refraction is equal to 4. Air is almost always 1. There are some times where it may not be 1, but for this problem, we're just going to assume that it's 1. So we already have our reflection coefficient. We have our omega. So we want to find the H field reflected. So to make this problem easier on ourselves, we can find E reflected first. So let me move most of this really quick. I'm going to just write this off to the side. So our omega is equal to, our omega is equal to 10 to the 11. Our refraction of the glass is 4. And our reflection coefficient, 1, is equal to negative 0.6. And we can also find, before we look for ER, our transmission coefficient, which looks like this. To find this, we just do 1 plus our reflection coefficient, and that will give us 0.4. All right, so we have a few of the key building blocks to start this problem. Off to the side. Our basic setup, since we know that we have the E incidence, or the electric field incidence, we can write E R vector is equal to x hat. And the reason why we say x hat is because the E reflected field, the electric reflected field, will still be oscillating on the x plane, even if it hits this medium. So we can say x hat 1.5, our reflection coefficient 1, cosine omega t plus k. The reason why we say plus k is because the direction of propagation will be the exact opposite of the incidence, because this wave is bouncing off our glass plane here. And then we can just fill in for ER. So we get ER x hat 1.5 times negative 0.6 times cosine 10 to the 11 t plus k y. So then we get E r vector r negative x hat 0.9 cosine 10 to the 11 t plus ky. And we want to solve for k. We can denote this as k1, and k1 is equal to omega over c. And then our omega over c is going to be equal to 10 to the 11 over 3 times 10 to the 8, which will give us a total of 333.3 meters to the negative 1. So then our E, R, is going to be equal to negative x hat 0.9 cosine 10 to the 11t plus 333.3 y. So that's our E reflected. So now that we have our E reflected, we can find our H reflected. So in order to find the H reflected, we have to divide our 0.9 value. We have to divide that value by eta naught. So then we get HR, H reflected, is equal to negative z 0.9 eta naught cosine 10 to the 11 t plus 333 y. Eta for this problem is equal to 377. So then our final answer will be HR vector negative z hat, can't forget the hat because it's a unit vector, is equal to negative z hat 2.39 cosine 10 to the 11 t plus 333 y milliamps per meter. So that's the units for our H field reflected. We found the direction of the H field reflected by drawing a graph. So if I was to draw this out, we'd have x and the y-axis. And if I draw out our ER, it would be in the negative x direction. And if I was to draw the K, we'd get KR pointing downwards. So by looking at this XY plane, we can determine that the HR would have to be in the negative Z direction, like this. So that's why we say negative Z hat. And we're determining this using the right-hand rule. So if we have our index finger as our ER, we can point, and then with our thumb as the KR, we would see that our HR would be in the negative Z. So that's how we're finding the negative Z hat for our H reflected. For this next problem, we're going to be answering Q2. Let me just clear some space. And what Q2 is asking us is, what is the first transmitted field inside the glass? So our setup is going to be the electric field transmitted is equal to x hat 1.5 tau 1 cosine times omega t minus k2 y. Our propagation direction is going to be the same, and our field will be still oscillating on the x plane. So that's why our x and our sign here are the same. So the two things we got to solve for are k2 and tau 1. Tau 1 we already solved for, so we have 0.4, and that will be the transmission coefficient. And to solve for k2, we can say k2 is equal to omega over C n, n being the refraction coefficient of the glass. So that gives us 10 to the 11 over 3 times 10 to the 8 times 4, which is equal to 1,333 meters to the negative 1. All right, now we just plug this in. So then we get ET is equal to x hat 0.6 cosine times 10 to the 11 t minus 1,333 y volts per meter. And that's the usual unit for the electric field. All right, so we just entered Q2. Now we're going to solve for how much power is being transmitted through the block. So our first step is to find gamma 2, or the reflection coefficient 2, when our wave is exiting the block. And to solve for that, we would do n2 minus n1 over n2 plus n1. This would equal 4 minus 1 over 4 plus 1. So we end up getting a gamma 2 is equal to 0.6. All right, so after finding that gamma, we can also find our power. Our power, PR over PI, is equal to gamma squared. And the reason for this is because the reflected wave and the incident wave are in the same medium and with the same impedance. So the power ratio can be rewritten as gamma squared. This is important for us because if we want to find the amount of power that's transmitted through the block, we can look at this ratio, P transmitted, power over power incidence. We can say that because of the law of conservation of energy, this PT over PI must equal 1. So PT over PI plus PR over PI must equal a value of 1. Well, we know what we can replace PR over PT with, and that would be gamma squared. And what we can write is we can write power is equal to the equation 1 minus gamma 1, the absolute value squared, times 1 minus gamma 2, absolute valued, squared. And what this tells us is the amount of power transmitted from going the air to the block for this one. And the second one will tell us the amount of power transmitted from the block to the air. So the wave goes through air to the glass and then glass to air. So that's why we have two of these multiplied together. And because they're absolute valued, we don't care if our gamma is 0.6 or negative 0.6. They're essentially the same value for us. So what we can do is we can combine them together. We get 1 minus the absolute value of gamma squared, value squared, and that comes out to 1 minus 0.6 squared, and then squared again. And what we end up getting is we get a value of power transmitted is equal to 0.41, and the power transmitted is going to be 41%. So we just multiply this value by 100, and that will tell us the amount that's transmitted through the glass, assuming that there are no multiple bounces being considered. Lastly, we want to solve for question 4 and 5. Number 4 is asking us, what is the wavelength inside the glass? All right, so what I can write is I can write lambda 2 is equal to 2 pi over K2. And if you remember from earlier, our K2 was equal to 1,333. So this basic calculation, lambda 2, gives us a value of 4.71 millimeters. And when you plug this calculation into your calculator, it will be over divided by 1,000, and that's because our lambda calculation would be in meters, and we want our answer in millimeters. 1, 2, 3. So that's how we're getting 4.71. All right, so that's our answer for the wavelength in the glass. And lastly, we want to find the wave impedance in the glass. So we can do that calculation by doing eta 2 is equal to the square root of mu over epsilon, which is also equal to eta naught over n2. This is basically saying that the wave impedance characteristic divided by the refractive index will give us eta 2. So if we do that calculation, it's 377 over 4, which is equal to 94.25. So that is our wave impedance of the glass. N2. And that's everything for this problem.